So anyhow, I want to see if Dave's out there. Dave, are you there? There he is. How you
Very,
doing?
yeah, very well, thank you, actually, Rich. Very excited about tonight's talk, by the way.
Yeah, me too.
Yeah.
And
Uh,
do you have any announcements for us
I
or
have one
anything?
important announcement, which
Okay.
is that not only do we have an extremely prestigious speaker this month, we also have an extremely prestigious speaker next month. Believe it or not, we have the chief astronomer for the Vatican Observatory, Brother Guy Consolmano. And Brother Guy has got by the way, he's an extremely nice guy, if you'll
Yes.
pardon the pun. And sorry, I can't resist. Somebody stop me before I do it again. Anyway, and Brother Guy, I'm going to be laughing at my own jokes now. It's a really bad thing to do, but that's okay. Rich does it all the time.
I'll just edit it out.
Please do. Please do. The idea of people watching this 1,000 years from now is absolutely terrifying to me. Anyway, Brother Guy's got hilarious and very fun talk. It's called Astronomy Ideas That Were Almost Right. For example, think circular planetary orbits, for example, which is so close to being right that it fooled people for a long time. And he's a great speaker, and it's very prestigious. And how often does EAS have somebody who knows the Pope personally?
He's a very nice person, and he's got a great sense of humor. And I met him here at Chabot several years back when he was here giving a talk for Chabot, and then was doing a book signing out in the rotunda. And he was telling me some of his astronomy jokes. So, so anyway, I'm sure we'll hear more of those next month.
Yes,
So
he also worked in Antarctica, recovering Antarctic meteorites, which is another story, but we'll talk about that later. And I'm going to
well,
shut up if I can.
Yeah, tonight's format is Dave will introduce our speaker in just a couple seconds now. We will ask you to hold your questions till the end of the talk, although you can build them up in the QA or chat section, and we'll curate those and present them to our speaker at the end of his talk. So thank you all for attending tonight, and Dave, I will turn it over to you.
Thank you very much, Rich. Tonight, it's my very great honor to introduce Jim Erickson, our speaker tonight from Jet Propulsion Laboratory. I want to be very brief about my summation of his career because he's done so many things. It's very, very hard to be concise. But Jim has worked basically on virtually every major legendary mission at JPL, starting with Viking back in, I think, 1973 or 74. Jim must have been like 9 or something like that, or very precocious. He's worked on Voyager, Mars Observer, Mars Reconnaissance Orbiter, which, by the way, has a telescope that was partially designed by a refugee from Telescope Makers Workshop, Galileo, Mars Exploration Rovers, and the Mars Science Laboratory. And so tonight he's going to be speaking to us about the 9-year exploration of Gale Crater and the climb of the Curiosity rover up Mount Sharp. And so without any further ado, Jim Erickson. Oh, I forgot to say that he was a manager of a whole bunch of those missions too. So, and he was a manager for Curiosity. And now I'll shut up.
Okay, Jim, your video is still off, so if you can hit your start video button.
I'm finding
there you go. All right, awesome.
Okay.
It's all yours, and I'll jump in case you're having any PowerPoint issues.
Okay. Right now, I'd like to just give a quick introduction to say I am, as of 3.5 weeks ago, the former project manager for the Mars Science Laboratory, and I've moved on to other jobs that are mainly involving managing managers of jobs. So it's quite a lot less interesting than what I used to get to do. So I'm going to be talking about what I used to do, which is managing one of the greatest space science missions of all time. It's Curiosity, and it's on a mission to find evidence for the past habitability on Mars, in particular, as he said, in Gale Crater. So now I'm going to try and turn on my presentation mode, share my screen, click on the right icon, And I hope I am now
Looks good.
presenting.
Yeah, you're good.
Okay. So, primary science question we're trying to answer is to explore Mars and quantitatively assess a region on Mars' surface as to whether it was a potential habitat for life, either at present or in sometime in the past. And what that means is, what was the biological potential then and now? What's the geology and geochemistry? We have to look at water, weather, and climate. We have to look at radiation levels and hazards. And that's going to tie into the whole Mars exploration by humans, finding out what is the safe levels of radiations, how can we keep an astronaut safe, what will they be exposed to, and what experiments have we done to try and figure out how to limit that exposure. So, what are the things you want to know if you want to think there was a habitable environment? You got to have liquid water. It's got to be there for a long time, where long time means millions of years. It's got to have the key chemical ingredients for life: carbon, hydrogen, oxygen, nitrogen, and it's got to have some form of energy for metabolism, something for the little critters to eat. Because sooner or later, you have to have something where the critters are so primitive that they're actually just basically eating different types of chemicals, and that's how they get their energy for them to grow and to evolve and to be eaten by other larger organisms. So that's what would make a place happen. Now, why did we pick Mount Sharp and Gale Crater? Mount Sharp is the central peak in the crater, and from orbit, from Mars Reconnaissance Orbiter and a few of the other orbiters that are there now, it was selected based on what we saw. In particular, areas like the clay-bearing unit, which was a layer of sort of like a level, a certain number of feet up the central peak, where mainly what we saw from orbit was clays in all of our instruments. We can actually, from orbit, look down and understand something about the chemistry of what we're looking at. So that's how we picked it. Now, we thought there was enough of it and enough varying parts that we'd have a chance to really try and understand what was going on. And in addition, we now know that Mars used to be wet. And from our exploration, we know it was wet for a very, very long time. And then, geologically speaking, it fairly quickly shifted to being a dry Mars. And so one of the things we really want to do is look at the interface between the clay units that were all formed with water into the sulfate units that were where it's dry and there is no water, and see if it's really sudden or very drawn out. And we'll talk more about that later. So the whole thing about Mount Sharp is there was the crater, the central peak, but then the crater was filled in with sedimentary rocks. As you'll see, primarily brought in by water and wind exposure. And they pretty much filled up the crater. And then they began scouring out with the winds in the dry period and sort of excavating back down to the earlier parts of Mars. And this is how we understand what the geology was, with, as always, just like in the Grand Canyon or anywhere else, the oldest stuff is on the bottom, the newest stuff is on top, with an asterisk here and there, because there's sometimes when there will be a relatively younger unit that will be formed. It will cover up some of the older unit, and then you'll have some of the new unit be worn away, and it'll look more like old, new, and then old again. So it can be confusing, which is why you need to have a lot of area to look at, a lot of area to go through, and have the right instruments to find out what you're doing. And we have a great set of instruments. We have both imaging instruments, a whole bunch of them. We have like 9 cameras on, one on the end of the arm that we use, and we can actually put it up against the rock and have the highest resolution images ever sent from Mars, as in the space of about 2 inches across. We can have megapixels on that 2 inches. We'll never do better than that from orbit. We have, let's see, going through the weather instruments that we have both wind and direction. Unfortunately, that was one of the first casualties of our landing. Sometime in the landing process, we believe when we were close to the ground and the jets were firing and kicking up rocks, we found lots of small rocks that ended up on top of the vehicle. And apparently one of them hit one of our weather sensors and knocked out one of the directions for wind measurements. So we had to get tricky on how we do wind measurements and how we know the direction. The velocity is fine, but we only got one vector. But we can turn the vehicle and take different samples, and then we can figure out where the wind is coming from. We've got the radiation instrument that we talked about, RAD. One of the cooler things we have is our laser firing device that can actually look at the little sparks that we generate when we fire the laser and then determine what the material is that we are hitting. And so from 20 feet away, we can explore Mars and do great detection of minerals and different elements without having to actually touch them yet. But we can touch them. And in fact, that's one of the things which we are the best at, because we not only touch them, but we can scoop up sand and we can drill into hard rocks, create a powder, sift it, and then drop it off to our various instruments, including both Chemin, which does analyzes chemistry and mineralogy, and to SAM. SAM short for spectrometers at Mars. And it's a collection of spectrometers that we can feed with the powder from the drill and actually do experiments on it and determine not only the chemistry, but what isotopes of the various elements we're looking at. We've got a laser-induced breakdown spectrometer in there. We've got a gas chromatograph, of course, and a few others. So we're really very capable, the most capable instrument package that's ever been landed on Mars. We have, I mentioned the nine cameras. We have one of them that's actually on the bottom of the rover pointing down. It was originally used for the descent imaging as we were hanging on the parachute and being lowered down. It was busy snapping shots of our landing site to be, so we have before and after pictures of what the rocket thrusters did to the landscape as we were coming down. And we can actually do what we call sidewalk images, where we sort of take a video of the ground underneath the rover as we drive away. So we also have one more instrument of note on the arm, and that's the alpha proton X-ray spectrometer. We can actually do chemical sampling for bulk mineralogy and material, and understand that by putting the APXS up against a rock and letting it fire protons into the rock, and by the X-rays that are given off from that encounter. We do spectrometry on those, and we can tell a lot about what the material is. So that's the chemistry package and everything else that we've got going on. And let's see, I think I've covered everything. So there is one. We have an active neutron sensor. Basically, the instrument that fires neutrons into the ground below the rover and looks for the reflected radiation from that. It also can be passive, where radiation from other sources is detected and we do the analysis of what's reflected from the surface. Either way, we're able to, among other things, detect subsurface hydrogen. And almost always we can tell the difference between when it's in the form of water, whether it's ice or liquid or anything else, and hydrogen locked into other mineralogy, which happens quite frequently. Okay, on to the next. So we talked about a lot of what the instruments are that we have. Some of the other things we have are things that allow us to say, if we really hit a home run and we find something that we think is a really good sample of what we think is real organic material, as in more advanced organic chemistry, we have a sort of check material on the rover deck, and we can drill into that, analyze that, make sure that what we're seeing from that sample matches what we put into it on the ground, so that we know that there's nothing going wrong with the instruments. Then we can take a sample, discover what we can about Mars on that, and then afterwards we can do yet another check of it with this organic check material and say, okay, it's still giving us only the things we brought from Earth. And that'll really give us a clean baseline to be able to prove that what we're finding is something that is just from Mars. We take a lot of care for this. Pre-launch cleaning of the rover parts extensively, including cultivating cultures every few weeks or so on the rover and different parts of it, just to make sure we really are keeping it clean. And then I talked about grinding up the powder and sifting it to get it the right size for the different instruments. SAM can handle bigger particles than Canon can. And we have to get them to the right size for each of the different instruments. And then, as always, we're very paranoid. We assume anything we send to Mars could break. And everybody who does any carpentry has broken drill bits. So we brought spares, as you might expect. And we have learned how to drop the broken one, grab the new one, and get back to work. And shortly before packing up to go to the Cape, this is what it looked like. They had finished the installation. The RTG was not in place. That was put down, that was installed at the Cape. But this is what the clean room at JPL looks like. Actually, it's the smaller of the two. And it's a place where one of the privileges of working at JPL is you can go down there whenever you want, take a look into the high bay and see the progress on spacecraft that are being built. So it's pretty cool, and they pay me to be there too. So nothing wrong with this gig. Now, I talked about the descent imager. One of the pictures that it got on the way down was when we dropped the heat shield, it was running and taking images. And this is just one of them, but it took quite a few. And we were able to measure the rotation rate of the heat shield as it dropped away, which was something we want to know so that we think we understand exactly what's going on with all of our entry, descent, and landings, whether it's way back to Sojourner or Viking or Mir, Curiosity, and now Perseverance. For all we know, we may have just made it, and we want to make sure that on future landings, we have margin and we have a high probability of landing, because we put a lot of our heart and soul into building these things and a lot of the taxpayers' money. So we'd like to make sure we always make it work. So let's see, we launched in November and took about 7 months to get there. And August of 2012 is when we landed. In this particular case, it was more like about 9 months. It varies between 7 and 9, depending on exactly what trajectory you're on and what part of the launch window you got off on. So, and here was touchdown, August 5th. And we had a nice science talk over at JPL on August 5th of this year. It's telling us some of the latest things that we found. And it was well attended, but not in person. It's still kind of a sad point for us, as it is for everybody else. We have learned how to actually do operations remotely. We are probably 90% effective in terms of getting as much science as we could. We'd like to do better, and that's why we're going to come back. We just have to work out how to do it safely. There are some things that have to be done in person. When you're actually bolting together a spacecraft, you can't do that in remote. You've got to have people come in. And so we've had about 25% of the laboratory still there working on all the new missions that are planning on being launched soon, whether it's our encounter with a metallic asteroid that's coming up called Psyche, or getting ready for any of the other missions. We continue to do work and get things done. And we do even better when we're allowed to get in there and rub elbows and get our hands dirty. And August 5th was celebrating 9 years on Mars. That's a long time. And yet, when I left last month, I was thinking about, wow, that was really quick. It just seemed like a couple of years, and it wasn't. So this is on Sol 84, was in the area where we landed, where we first saw the place that we believe from our instruments had a good chance of being habitable in the past. And since that time, as we've gone towards the central peak, Mount Sharp, and begun climbing it, we found many others where the evidence is really strong that if there was life there, it could flourish. Now, we aren't able to actually identify life unless it turns out to be something on the macroscopic field. If we find the dinosaur bone, we would know it. If we find things like algae mats, we're probably not going to be able to tell for sure that those are there. It's just not the kinds of instruments we have. We can analyze potential, but not reality. So that's for perseverance. Okay. We mentioned the descent rockets, and the area that we touched down in was originally covered over with a lot of sand and dust. But the rockets actually scoured the surface, got rid of all that so that we could see the original bedrock, which, once again, when you take a look at it, it's a lot of conglomerates, a lot of obviously embedded stones that have been reworked into different materials. Everything we really wanted to see. Close-ups of some of them, you can see both the pebbles and the conglomerates, and you realize we're looking for sedimentary rocks, because those are things that have either been they could have been deposited by sand blown dust grains, or they could have been by water flows. And these conglomerates indicate that the water flowed fairly strongly and for a long period of time, somewhere between ankle and hip deep. And they tell that by the size of the boulders it gets transported. I would call them more like pebbles in this particular case. But the sedimentologists are experts in this. They have a lot of experience with what we find on Earth, and they can translate their expertise onto the surface of Mars as well. So this was the first time we deployed the arm over at Yellowknife Bay, which is, like I said, the first time we found something that we thought was the bullseye. And where there could have been life in the past. This is an example of some of our sampling. The drill bit's up on the left. It's not like a spiral tip drill bit. It's more like a hammering chisel, because we actually can hammer it, and we do. We percuss and pound it into the surface as it's rotating and grind it into a fine powder. There's a tray that you see. It's actually can be used as a scoop as well as that, and take the piles of sand and things off the ground and then contribute that as a sample to the instruments. And we sometimes do that. But if you look at the two drill holes, the test one on the right and the first real drill hole, these look pretty big, but in actuality, that hole is only about the size of a dime. We don't need to get a lot of material out of it, but we need to get something on the order of tablespoons worth so that we can feed both the two instruments that do the sample. And we'd like to try for like 4 tablespoons, but we can get by with 1 and be stingy. So, and if we really think it's important, and we've done it in the past, we just move the drill over 2 or 3 inches and drill another hole, because you can look and say, well, the rock looks very similar between that area and 2 inches over. So let's drill in there and get what we believe to be a second sample. And it works out pretty well. Examples of this. Now, if you look down the side, there's 2 things you might notice. One is these wavy patterns. And what those are is they're cracks in the rock where water deposited some other mineral. It might be that the water was high in sulfates and some of them were deposited in the cracks, and that's what you're seeing. In this case, that's exactly what it was. If you take a look slightly to the right of that, you see these little black marks in a row, and that's where we fired the laser at the side of the hole. And if you look down about number 5 from the top, we hit one of those veins. And so we were able to tell exactly what the material was that was in those, and it was a sulfate material. But we also, as you can tell, we got 5 samples on that didn't have that, so that we knew what the base rock was for that. And there's a 2 millimeter scale bar for you. So. Okay, so we believe and have published the papers, and it's been very well received, and there are discussions, but there is no real disagreement that we've determined that ancient Mars was capable of supporting life. If life was there, it could have flourished and thrived. We found water, it wasn't too acidic or basic, the key chemical ingredients required by life, and sources of energy for the very primitive organisms to have eaten, so to speak, and gotten their energy source from. And that was both from Timon, finding the clay materials, and Sam and their spectrometers finding the basic chemical ingredients of life in those samples. This is a good way to say, well, how does Sam do this? How do you take a rock and do spectroscopy on it? In this particular case, what we do is we take the material that we've ground up, put it in a little cup. They've actually got 72 of them in their wheel. And then we move that cup into an oven. And we heat it up to as much as 1,000 degrees centigrade. And it turns out that minerals will break down at different temperatures and release constituents. As an example, if you look at the 200 centigrade, there is a H2O peak where a lot of water was driven off between the 200 and 600 degrees. And that was where most of the water came out. But there was another peak at about 800. And the answer is different minerals will release their waters at different temperatures, depending on how tightly they're bound into the rocks. And that gives you an idea of what minerals were the two that caused those two peaks, both the one at 200 and the one at about 750. And you get more information from Cameron. You get more information from some of the other mass spectrometers that are in there. You get more information from what other gases are driven off and at what temperature. CO2, oxygen, sulfur dioxide, hydrogen sulfide. All of those play a part in the graduate students' challenge of taking all those different peaks and trying to determine what set of minerals could be in the rocks that we ground up that was sedimentary rocks in the first place, meaning the original rocks were broken into little pieces, washed down into some river tributary or a delta, and then over billions of years became a sedimentary rock that we just rolled into. So it's got a lot of stuff mixed in it. And that's the job of the people studying this, is to know how to take the libraries of rocks, what gases they drive off at what temperatures, look at what we see and try and do the inverse. Try and figure out, okay, if we have this, it had to have been both these rocks and those rocks and these minerals, and make the case that you actually do know what the minerals are that was in that sample that we drilled. And that's quite a challenge. And we've got a team of almost 500 scientists now that work on this program, and they all do different things, but they're all pretty much devoted to finding out those key ingredients. What's the habitability, one way or another. Here's the bottom line. The geology, fine-grained rocks that we saw there suggests that John Klein, which is that location, was at the end of an ancient river system or within an intermittently wet lake bed. There was water that flowed. It was enough water to stay wet for a long period of time. Mineralogy indicates sustained interaction with liquid water, not too acidic or alkaline, not too salty, and conditions were not strongly oxidizing. If it's too strongly oxidizing, even if you had life, it would be destroyed by the oxidation. So you're looking for areas where there wasn't that. Got to have the key chemical ingredients like we talked about before. And then enough minerals in various states of oxidation that could provide a source of energy for very primitive organisms. Not the kinds of things that eat other organisms, but the kinds of things that ingest chemicals and based on getting a donated electron and taking some of the energy from it and donating it back to another chemical. That's how they ate. So not quite as great a meal as you and I might like, but you got to start somewhere. This is one of the interesting challenges. We came to a point where it looked like our way forward was blocked by a giant sand dune between two hills, and we didn't find a way out that didn't take us miles and miles out of our way. And we took a look at this and we said, well, this could be interesting. And if you look at on the left side, where there's sort of a line that goes across the tracks, that's where we did our first toe dip. Turned the wheels sideways, dug a little bit, and measured how much force we could get before we began slipping. And that gave us enough confidence that we just drove up and over the giant sand pile and over to the other side and saved maybe 8 months, 9 months of going on a detour. That's not to say it would have been a wasted effort, because I think anywhere on Mars you go, you're going to learn a lot, depending on the instruments you have more than the area you're on. So, and then we came to the Kimberley. And they call it a striated unit because it's basically a lot of different fine layers that were deposited in the geological past. And then things have happened since then. Examples, there's been deformation of the surface. On Earth, it would be principally by things like mountain building, earthquakes, things like that. On Mars, you can get similar things, particularly in the distant past. But they were all originally nice and flat when they were originally down in the bottom of a river or in the bottom of a lake. And this is the possible lake deposits at the base of Mount Sharp, the central peak, and some of the ways that it could have been deposited. And the answer is probably all of the above. If you're in a lake, you're going to get fine material that's going to wash down through the river system into the delta, and then it'll settle down on the bottom of the lake and begin depositing more and more over the years. But when the rivers are busy cutting through the soil, excuse me, a second. Just like in the Mississippi, the rivers will fork and form deltas. And as the rivers cut more and more material off, the delta may start advancing. And the deposits will start filling in the lake and covering over some of the original deposits that were laid down when it was the lake with parts of the delta. And then finally, the rivers are going to be washing new stuff as they cut deeper into where the original river deposits were. And they're going to be scouring that out and carrying it into the delta, which will put it down in the bottom of the lake. So you're going to end up with a lot of different things from different materials that's in there. And difficult to tease out exactly what the history was, but that's why we were there. So far, we have climbed and, well, actually, first we went down in altitude when we went over John Klein. And then after we explored there, we started our upward trend. And between the two of those, we've done over 460 vertical meters of bedrock, meaning we've sampled periodically all the way up the hill, made mostly of fine-grained and finely layered sedimentary rocks. And we believe that it's formed from mud in the ancient lakes. Mud cracks are evidence of when, just like here on Earth, when the mud dries, like in a dry lake bed out in the Mojave, it cracks because it's shrinking. And if the right circumstance exists and something wet comes through that's a different material, you can get cracks which has a different mineral type in it that were deposited after the original cracks were formed, and it just sort of filled it in, as you would expect. The veins of minerals are deposited from the groundwater that flowed through the sediment after it hardened the rock, like described. This is another example of how that happened. Now, if you look at the white layers, which are about 2/3 of the way towards the left side, you'll notice that they're standing up higher than the surrounding rock. What that means is they're basically a harder rock that flowed into and filled the veins. And then when this area was scoured by the winds, it was harder to break that down than the intervening material. So that's why they're sticking out like that. It's interesting, but very explainable. Okay, after the lakes disappeared, things began to dry out. Sand dunes covered the area. These sandstone capped buttes are all that is left of the sand dunes that originally covered the whole area. They're more resistant to being scoured away by the wind. So wherever they are, they protect the underlying material. And that's one of the things that we did to try and make sure we could do good measurements of what the ages of some of these rocks were. We wanted to find areas that were protected by these kinds of caps, and then drill into them and do isotopic surveys to say, at what point was that sandstone laid down and no longer had contact with the atmosphere. And so that was one of the experiments we did. Okay, now you guys lucked out. This is an accurate chart. If you had waited till next week, it would have been 33. We're getting ready to do drilling again. But this is just sort of our pride wall of all the different drill holes that we've made where we actually did sampling. We don't count the test drill holes that we do. But it's a nice rogues gallery. So, and more to come. We have found a diverse set of organic carbon-based molecules. Now, when we say organic, we're talking about like organic chemistry, not like organisms. Organisms are made up of organic chemistry, but they're more long chain molecules that are very difficult to keep around for a long period of time, and even harder to analyze when the way you have to find them is by heating them up hot enough to break down a lot of things in order to find out that, oh, well, we've got this piece of something and this piece of something, and they could go together and become this long chain organic molecule, or maybe this one. And then we kind of cheat. We know that some of these compounds can grab sulfur atoms, and that actually protects them longer if they have one of those than if they don't. And the other way we cheat is, we talked about how we use the temperature to drive off gases from the rocks, but we also have some chemicals that we brought along with us that we can put the sample in the chemicals, and they will actually preferentially bond to long chain organics and protect them as we do the same heating and analyzing. So it sort of is a kind of a key that we lock into organic materials, and then when we do the analysis, we know what we put in there, and we know what it attaches to, and we see what comes out. See what, it's kind of like fishing. The bait is the material we provided, and what it connects to is what we're trying to catch. And we're really trying to catch pieces of very long chain organics that we recognize and say, well, this is part of, this is not really, but for those of you who have seen a sugar molecule, you can find pieces of the sugar molecule and you can say, well, I got this piece and this piece, so I bet, because I see all the pieces needed for sugar, that's what it is. It's sort of the same thing, but with many other choices for the scientists to look at and to figure out which one is which. It takes months for these guys to actually do the work on every sample and try and do enough to say, should we hang on and do some of the really interesting experiments that we're saving for when we think we might have found really long chain organics, something approaching that necessary for life, or whether it's close but no cigar. So right now, they haven't told us they found anything that's the bonanza yet. Now, everybody wants to know what's the temperature on Mars. And the answer is, just like on Earth, it depends. Gale Crater is towards the Martian equator, but not really at it. So it's not the hottest places on Mars, but it's much better than other places you could land, like the polar caps. When you start talking about 120 degrees below zero, that's a little chilly for people to survive. But if you take a look at when you're talking about maybe 30 degrees Fahrenheit, People live in that environment. So it's not that bad. But you notice there's a very long bar on Mars as far as how cold it is at night and how warm it gets during the day. You're talking about 100 degrees Fahrenheit between the two. On Earth, it's in the 20 degrees difference, not 100. So you might survive pretty well in the daytime, but when you're talking about minus 100 degrees Fahrenheit every night, it's going to be tough. So now, this is a series of images which captured a dust devil going across the terrain. I hope it's showing up as well as for you guys as it's showing while I projected. I always worry about tricky things like animation. So one of the things that these dust devils do, obviously, as they're spinning, they're actually picking up dust off the surface, bringing it into the atmosphere, and then it'll settle out, a half a kilometer away from wherever the track was, because it's very fine dust particles take a while to filter out. Now, for curiosity, it's an interesting natural feature that we want to study. For the MER rovers, it was something that extended their lifetime for years. Is having dust devils and nearby, just passing close to one, would clean off the rover's solar panels and give it another few months of life every time it happened. So that was a big reason to why Spirit and Curiosity lived so long. Okay, we're talking about the Twilight Clouds. This is something that we look at, and we observe these clouds, and they're either water or carbon dioxide ice, very thin, and similarly sized small ice particles results in iridescence. The sunlight gets refracted into different colors, and on the color images we can see that. But we have to do image stretching to bring out the colors in it. So the unstretched version is what you see in the main picture, but the same images is then stretched to show the different colors that those ice crystals bring to it. Okay, now this is one of the curiosities that we think we're on a good footing to solve now. We detected a very strong diurnal and seasonal variation in atmospheric methane, as well as occasional large spikes. Example of the large spike is on the right-hand side, upper right, blue dot, error bars, and that's one that doesn't follow the yearly cycles that we saw. Now, each color was a different year, but they all correlate well enough from this point of view within the uncertainty. And the variations are basically seasonal changes in how much methane seeps out of the ground from the subsurface versus the daily mixing with the air. Now, the big ones that show up on the, like in the upper right, that's where there was a local event that happened while we were there. And in that case, it went away within 3 days, the turnaround time to get set, do another measurement, and it was gone already. So that's part of it. Now the challenge is the trace gas orbiter for ESA is a great instrument for detecting methane in the atmosphere. And at the time when we were detecting all of this, it wasn't seeing any. It basically didn't show any methane. And yet we did, and we repeated it year over year. And then somebody came up with the idea of, oh, wait a minute, what do we do differently? Well, we take our measurements during the day when we have power. TGO has to take them at night. So we did a few experiments because they're very power hungry. and did some of these analysis at night. And we did a daytime measurement, a nighttime measurement, and a daytime measurement. The daytime measurements had noticeable methane. The nighttime measurement didn't have any. So what happens is all the methane that's generated during the day from the warm surface, we measure it right away as it's coming out. But by the nighttime, it's all gone. And that's why they didn't see it. So that's a great explanation. It fits all the facts. And now we have some discussions to have between the instrument teams on the different missions, that not just why it's different, but why is it different? What does it tell you about how fast the methane has to disappear? And now they have data points to say, okay, we can figure that out, as opposed to arguing about whether it really was there or not. Science advances. Now, I talked about Mars human missions. And in particular, one of our goals is to measure how much radiation we get over years, both from galactic cosmic rays, energetic particles from the sun, both in cruise and at Mars' surface. And the answer is, during cruise, there's a lot more energetic particles that we measure by the vehicle. When we got to Mars, the atmosphere and the fact that half of the time you're shielded by the mass of Mars when it's at night, and you're not getting the particles from the sun. It's significantly less. However, 1 sievert is the maximum lifetime dose for an astronaut. If they go on a round trip to Mars and spend 500 sols on the surface, that's it. That's their one and only mission that they'll be allowed to ever do. And even that means they're getting to the maximum, and that's usually not where you want to be, because they're going to get some doses from things like X-rays when they break an arm or whatever that they're going to have to do. So one of the things we did was say, okay, if we get right up next to a nice cliff, how much does that cut back on the radiation we see when we drive 20 meters away and aren't shielded by that? And that'll give information on how effective the regolith is for protecting the astronauts when they get there. Can they use that as a radiation shield so they aren't getting as much while they're there? So that's data that they need for this purpose, and we're doing great at giving it to them. And every year we're there, we can get more and more precise data and information on how it varies with time. And this is an example of where we went up right to that cliff and used that to shield ourselves. Took into account exactly how much of the sun that we were getting shielded from, and looked at those measurements and characterized how effective that shielding was. And this may factor into how astronauts are protected with habitats. This is where we are. We're climbing up. And right now, if you look, you say we're at the star. We're actually about halfway between the star and where it changes in color from the green to the more blue, because we've moved on since we did this. But we're getting up to where we'll be going up to the Geddes Vallis Ridge. We're going to be well into the sulfates. We'll get to the channel, and we'll get a chance to look at what they call the green hue pediment, which is where a new material flowed down over the older material and covered it up. And that's an interesting feature. And we'll want to see what the interface looks like between the sulfate units, the clay units, and the pediment. So currently, that's what we're doing. We're We're getting really close to the sulfates. We're continuing to measure every basically 25 meters of altitude because we want to catch the transition. We want to understand whether it's fast or slow. A lot of altitude of deposition or just a little bit. And whatever we see, it's going to represent a major change in environmental conditions from a wetter to a drier climate, which we know it happened, we just don't know how and what it was like. Now I'm going to do a little bit of bragging about my team. How we work this, how we do it. We have to actually basically build a program every day of what we want the rover to do. And then send it off to Mars. It takes about 15 minutes or so each way. So the process is we get a downlink, we look at it, make sure the vehicle's safe. Scientists get to say, okay, seeing all this, I want to go do that. I want to drill here, or well, I want to drive over this other rock and hit it with the laser. We build a program to do that, send it up. When daytime comes on Mars, it executes while we're sleeping. And then the next day, we get another download, see what we did, do the same process all over again, and send it up. And the good days is when daytime on Earth matches nighttime on Mars. For the first 90 days, as we went through the cycle, where every day, the Martian time got 20 minutes further, 40 minutes further and further behind. So that after day one, say Monday, you're starting work at 8 o'clock. Tuesday, it's 8:40. Wednesday, it's 9:20. Thursday, it's 10 o'clock. And pretty soon you're starting to work at midnight and working all night and getting it out. Well, after about 3 months of that, we quit and did it in a more sustainable route where we do that for a while, but then when it gets to be more than about noon that we're starting, we skip a day and plan 2 days and get the data back, and plan 2 days and get the data back, so that it's not quite as hard on us. And in the process, I mean, like I said, get the downlink in the afternoon, we process it, we assess it both the science and engineering teams. Engineering teams are looking to say, did everything happen that we asked it to do? Did anything go wrong? Did we have any anomalies to look at? Did we use the amount of power that we thought we would? Either less or more is important. And did we get as much power from the RTG as we expected? And given that, they say, okay, science teams, here's your parameters for what you can do, how much power you have, how much time you have, how warm the inserts are going to be when you get to start planning. And they build that, turned it into a sequence. We do extensive validation and integration, uplink it, and start it all over again. And everybody's got to do it right, or else bad things happen on Mars. And that's what we don't want to have happen. And this is the team as of a year and a half ago, prior to the pandemic, that did all this. Now, this is almost exclusively the engineering team. Our 450, 500 scientists are spread out across the world. Intern teams are at Goddard Space Flight Center. They're in Canada. They're in Germany. They're in France. Everywhere. And they all contribute, and we all work together. Those teams had a head up in learning how to work virtually because they were already doing it, and we were doing it with them. And that was actually the experience that helped us in only a week make sure that we were prepared to go virtual and do everything from home. And we missed one day, and that was it. And the second day, we were up and running and haven't lost any since. So I think now is a good time to stop for questions.
Great, thank you so much. First, Dave, I'm going to have you jump in if you'd like.
Yes.
And you often like to start off with a couple of compelling questions. I don't know if you have any tonight or
I
not.
have zillions of questions, and I have to try to exercise.
Why don't you pick the most compelling one,
Well,
so we can get to the ones from the rest of our audience?
it's kind of two that are kind of tied together. So
Okay.
forgive me, Jim. So Jim, I was looking at where you are in the crater right now and where you're going to go. And I see that you're not, so far the plan is that you're not going to go all the way up to the top of Mount Sharp, if I'm interpreting that diagram correctly. Do I have that right?
Yep.
However, so one of my questions is, starting at the elevation that you originally started at and the elevation where you're going to end, what percentage of that elevation are you at right now? And tying in with that, could you go to the top of Mount Sharp if you wanted to go to the top of Mount Sharp?
The second one's really easy. No, we can't go to the top of Mount Sharp. As you go higher up the mountain, it actually gets steeper.
Mm.
And it gets covered with dust, not millimeters or centimeters like we see here, but meters. And
Wow.
we can't drive uphill through that kind of stuff.
Yeah.
Well, there's a point where we can't go any further, even if we wanted to. And we'll find out where that is. Right now, I would have to say we're probably somewhere in the neighborhood of 70 to 80% of our eventual altitude.
Mm-hmm.
Now, that is based on our estimate as to when we'll get to the point where we can't drive any further. And
Say that again. Didn't get that.
we will get to some point where we can't drive any further.
Yeah.
And it may be that we'll get to go higher than we think, or maybe we won't get to go as high as we think. It'll be what Mars says we can.
Yeah.
So.
All right, thanks. Gerald asked, and he's recalling that there were problems with the wheels being punctured, which I didn't know about. What did you learn from? Yeah, what did you learn from that?
We learned to have perseverance, have tougher, bigger wheels. That was for the program. That was the bottom line.
Yeah.
They said, fix this problem. For us, it was how do we deal with this? Because it's not like we didn't bring any spare wheels, and that people actually asked us how come, and it just wasn't foreseen that we'd need it.
Well, you could have brought spare wheels, but it was the pit team that would have been a tough sell. So when we first started seeing this, we kicked off a massive test program to say, how come in all the extensive testing we did, we didn't see this on Earth? And the answer is, we didn't actually test for really sharp, really hard rocks, the kinds of things that are more like an obsidian knife wedged in the ground than boulders that we would have to drive over. We can drive over boulders very large, up to almost the size of the vehicle, but we wow. And it wasn't any one thing that did it, but going over a bunch of these things and not knowing that we were taking damage until the first pop through. And then we said, okay, what's going on? We're in trouble. You guys start analyzing this, and we'll start saying, well, we want to avoid all rocks. Couldn't do that. And it turned out that we had gone into an area where it was pretty much the worst we ever saw. And we found it, got our way into that. And it's sort of like we're in the briar patch, really good. And how do we get out? And we spent about 6 months getting out.
Wow.
Slowly, carefully. Instead of driving 100 meters, we drove 6, 4, 2, trying to find the area that got the least damage possible. Well, I gotta say that I had a similar experience and reached similar conclusions driving here in Oakland. And the thicker wheels are the solution. Sam asked, we're clearly searching for carbon-based life like we see here on Earth. Do we have any way on any of these spacecraft
of detecting the possibility of other types of life?
You know, as they keep telling us, it's hard enough to find evidence for the carbon-based life, much less posit some other type of life that we don't even really know what it could be and recognize it. So right now, that's not in the cards. It just, we know the question. We don't even know how to approach answering.
Yeah, it's a whole different science, right?
Yep.
Gerald was wondering if the rover technicians are still issued executive jewelers Mars watches, even though they've got a more sane schedule for their workday.
I'd like to, for the record, say that everyone bought their own. We did not get them provided. And when the jeweler wanted to give one, we had to say no. And so I had to buy mine.
Fair enough.
Yeah. It's not really necessary, but it was kind of cool. So.
Well, Gerald was bragging that he has one. I don't know where he got it. I'll have to ask. I'm going to have to ask him about that.
I'm green with envy here, or
yeah.
red with envy, I guess.
What is the nature of the power supply? This is from Chris. What are the nature of the power supplies and power storage on these rovers? I mean, I presume you're using lithium batteries, and the power supplies are kind of standard power supplies for the buses that control all the experiments. It's all solar. How much time it's not all solar? You
right.
shook your head no. So what have you got?
We have an RTG.
Ah.
Isotope thermoelectric generator.
I didn't know that.
Basically, it's a lump of plutonium that is naturally warm from ordinary decay. It's wrapped with thermocouples, and the difference in temperature between the hot plutonium and the cooler fins that you see on the RTG, that produces a tiny bit of electricity from each of those thermocouples. And from that whole chunk of plutonium, we actually, when we landed, we got 130 watts out of it. So you could power 2-3 light bulbs, and that's it. But we have very efficient systems.
Wow.
So you've got that combined with the solar cells, and that gives you enough. Or you have no solar cells?
No solar cells.
Oh my gosh!
It's not quite
true. I had no idea.
They do have a solar cell that basically is trying to just measure solar input.
Got it.
It's not
that doesn't count for power though. Okay, I've learned a lot. Battery. Yeah.
And we sleep a lot at night. We're not lazy. We're saving up energy for doing things in the day.
Well, that answers my question, because I was wondering what techniques you were going to be using to keep dust off the solar cells, like some of the other missions have had challenges with, and you don't have that problem.
Nope.
So that's nice. Great.
We have our own.
You have other problems, right? Let's see. Have you found anything yet in the results that you feel bridge the discovery of standard organic chemistry compounds versus life longer chain compounds? Is there anything where you're saying, aha, this is a maybe?
All I can say is if they have found that and are continuing to analyze it to try and decide whether to publish or not, they haven't acted as if they have, because they didn't say, okay, it's time to pull out the wet chemistry and do the check material and make sure we can sense everything we brought from Earth, do the sample, and then sense it again. They haven't asked for that. So right now, they're just looking at, admittedly, longer and longer chains of chemistry that they've been able to definitively publish, but not what everybody would be cheering in the streets for. Not yet.
Okay. We had one question which was kind of asking for some clarification. You talked about the sanitation process, not only of the spacecraft, but the sampling process itself. Is there anything you want to add on that topic, or to help us understand how you maintain the purity of the samples that are taken to make sure that you are measuring Mars only?
Well, we have an advantage in a way. If there was anything in the sample chain that came from Earth, and we didn't see anything in all the sampling that we've done, both looking for it and when we do our experiments with the Martian stuff, if we saw anything that looked like an Earth type thing, we would know it, and we would then begin trying to figure out what was going on. But every sample we took, every drill hole we made, further cleaned the vehicle.
Yeah.
Just like, go camping in the desert and you wash your pans with sand.
Right.
That's what we were doing, and we've done it for years and years and years and years and years.
Wow.
Sure. So the quality and certainty get better and better with time.
Yep.
Makes sense.
But at the same time, sometimes what you see is, say you take a sample today and then move on and take a sample a week from now from a different location. You do have to be careful because, yes, you've cleaned out as best you can the drill, but there's no brushes to clean it. So you basically rotate it and shake it, and all the things that you think of to get dust and dirt out of it. But is there some material still sticking in that you then measure along with the next week's sample? And the answer is probably.
Probably, yeah.
So, and we look for that, and they say, well, we're seeing a tiny bit of this, but that's what we saw last week. So it could just be a little bit of holdover from that. And if you do another sample and you see it again, you say, well, maybe not. Maybe it's a little bit of that that's actually in the rock.
Because you would expect to see less with time, right?
Yep.
Yeah. Rich asked, what's the leading speculation on the methane that you're detecting during the day?
So I actually didn't mention that at all in terms of what's the source of the methane.
Exactly.
There's two possibilities. One is what they call serpentization. It's a process where if you put water on certain minerals like olivine, you can actually have it drive off methane just from the rock and water. And from our DAN instrument, we know there's a lot of water under the surface, both in the form of things that have bound into rocks and something that looks a lot like there's some free water available. We can't tell ice or liquid water. And it may be ice most of the year and only liquid in the summer, or only liquid in the day and not in the night because of the temperature difference, and that's why we don't get any methane at night. But that's one way. And then, of course, there's also the microbial life theory. And from the methane, we can't tell. Methane is methane.
Right.
Both of those are plausible. But since the one is so attractive, you have to resist thinking it's that and say, how do I prove it's not just being driven off from the rocks?
Yeah.
And that's really hard. And right now, nobody's publishing anything that says how to do that, much less having us do it and prove it one way or the other. So could be either one. Right now, you have to think of horses rather than zebras.
Yeah, or cows,
Yeah.
as the case may be. Let's see. There's one here. On the Earth, before there were animals to graze on them, it appears that the bottom of water bodies would be covered with a Monaran mat, I've seen papers about how you can see evidence for these mats. Have you been on the lookout for that? Frank asked this. I don't know what a Monaran mat is.
It's these microbial layers of stuff in mats that they see in the right conditions. And the answer is yes, we're looking for it. There is some evidence that some people have seen that is disputed. So it's not anything where everybody says, yes, we've seen one. It's more like, well, this looks kind of like it, but it's not quite right because it's one thing or another. So, and then other graduate students will say, no, it couldn't be. If it was one of those, you'd have this too, and you don't see it. So that's one where they get to argue for a long time before they say, yes, we've proven it.
All right, and a good closing question from our Facebook audience. Donald asked, well, he said, first of all, great talk, thank you. What do you think the end date of the mission will be, and what will be the limiting factor that has you decide to close up shop?
Okay, if you'd asked me this 5 years ago, I would have said, I think the wheels are going to get us, and it'll be in 2 years. Well, I've got great people working for me, great engineers that not only do great testing, but they also figure out amazing things that we can do with our vehicle that it couldn't do when we launched it. So as an example of one of the things we do, we have ground software now that actually characterizes rocks automatically and shows up on the rover planner's screens as red, yellow, green, green being go here, red being don't even think about it. And besides that, we actually uplinked new software on the vehicle that basically says, if you come to a particular rock, any rock, and you begin climbing it, you then slow down all the other wheels. And you say, why would that do anything? When you have a vehicle where all the wheels go at the same speed, and you have one wheel that wants to go up over a boulder, that wheel wants to go, it's got to go farther than the others. Because as you drive over a rock, you do that, and that's a shorter distance is a straight line, and that's not the shortest distance. So it's actually being dragged across the rock by the other wheels. So the software now says, if you tilt and begin going up a rock or something, slow everybody else down and let the wheel roll over gently, so that we weren't doing that anymore. And quite frankly, we have slowed the damage by probably at least an order of magnitude, to the point where right now we think we'll be able to drive on these wheels until we run out of RTG current.
Wow.
So it's not the thing that we're going to get.
That's going to last a long time too.
Yep.
Yeah.
Well, actually, we started at 130 and we're down to 80. And it takes a lot of power just to have the computer be turned on. And then you've got to warm up all the devices like the wheels and the instruments and the arm before you can use them. And you do that by taking power out of your battery and the RTG and heating them up. And so there's sort of a minimum just to stand in one spot and talk to the earth. And we're doing everything we can to push it to the right and make it as far in the future as we can, but it's coming. 5 years, 7 years, 4 years. I'd say more like the 7, because like I said, I used to have a great team working on these problems, and they've come up with lots of good ideas, and we've already pushed it to the right a bit. So,
well, that's still a long time left. I mean, another 7 years is pretty tremendous if you can get it.
What's going to kill them.
Yeah.
So.
All right. Well, thank you.
I've got two more questions to
Yeah,
ask.
go
I've got
ahead.
an email. Can I ask one?
Yeah.
All right. I'm torn which question to ask because I think they're both very interesting questions. On the human interest side, I'm going to ask the easy one. Did you guys have any trouble shifting over to being on Mars time? And I want to get this clear in my mind. You guys were working on Mars nighttime, right? And you would sleep during Mars daytime. Is that correct?
That's correct.
Okay. And did you have any trouble doing the shift, that 20 minutes every day? How did that work personally?
It was ugly. It was more ugly on this like day 77 than on day 2. Day
Yeah.
2, you were so excited. It was hard to sleep anytime.
And there was probably a novelty to it as well at
Right.
that point. Yeah.
But it got really old, which is why we stopped. There was a lot of people that it took a while to convince them that you couldn't just hire more people and have these guys go off for a 2-month break and then have the other guys, which we didn't have the money for, come and do it. So, and then there was my favorite solution, which was we were going to put everybody on a cruise ship, and every day had to drive 20 minutes worth, and it would be fine. And they did not choose that option.
No, I suppose not. It's creative. That's very creative.
Mars tour. I love it.
Yeah.
And you had 2. So what's the other one?
Oh, the other one was
for it.
your terminal location that you showed in the chart, which looked blackish up there, halfway up up Mount Sharp. And I was wondering about what is the geologic character of that, and what's it like, and what are you guys expecting to find there?
Okay, we think that that whole Geddes Valley is a valley carved by a river. But there's sort of like lumps and bumps and areas that meant that towards the end, something, with less water, it couldn't come down the whole valley. It had to cut rivulets. And sometimes it looks like it couldn't cut them. And we'll have to see what happens. So it'll be interesting.
And you'll get there how long from now, do you think, roughly? It's money dependent. Right now, if I had this current budget for the next 5 years, I would say for sure in 2 years, we will have gotten to the point where we think we'll be stopped. We may be able to go further, like I said, but and then we could spend another few years going left and right, and maybe going back to something that we didn't get to see because we had to pick between 1 or 2 things, and now we could take the other 4. Yeah.
And all of that. But that's going to be something which every 3 years they're going to ask us, well, what are you going to do the next 3 years, and how much money is it going to take, and tell us why it's worth it.
How much money were you talking, just out of curiosity? For roughly?
No pun intended.
Generally, we're talking somewhere in the neighborhood of 45 million a year. So it's not like
No, so much.
a tiny amount. It's a lot of money.
Of the total expenditure, it's like
You got a lot of bang for the buck here.
yeah, crowdfunding, crowdsourcing.
Yeah.
I'll send in some money.
Well, we have yet to have our first million come under the transom. So anyway,
All right.
NASA works with us. They do their best.
Yeah.
But there's so many interesting things to do for NASA.
Can I ask about the sky crane? I'm dying to ask about if you had any skepticism, but I heard this idea and I thought you guys were all nuts, to be honest with you.
That was pretty much the standard response. Until we spent months and months and months explaining to them why it was the right answer. So.
And I know you tested the hell, or you tried to test. I've seen some of the video of your tests, and but it still scared me.
Well, it's interesting. We test a lot of things, and we like to test to failure. Because then we have a data point rather than, well, it's at least this good. But if we know we have a failure at 35,000 cycles on this part, you know what you have to be scared of. When it didn't fail at 35,000 parts and you stop, you can fall prey to hubris into thinking, oh, we couldn't have just gotten lucky and stopped it just before it was going to fail. It must be good for many other times. But you can't do that.
Yeah.
So we have lots of failures, but usually they're because we wanted to, but not always. We had a lot of parachute failures that were not what we wanted until we got everything fixed. And the Europeans are now going through the same cycle of build, fail, test, fail, test, fail, test. And we're wishing them luck for their Mars mission that's coming up.
You guys did some of the wind tunnel tests, I know, over here at NASA Ames.
Yep. I've been to the wind tunnel there many, 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 many times in my career.
EDL.
I've even gotten to fly the simulator.
Ooh.
Yeah.
I better shut up.
Yep.
All right. Well, we have to end it, gentlemen. And
thank you, Jim. That was wonderful.
Yeah, Jim, it was a great talk, and thank you for filling us in on all the great accomplishments of this mission, clearing up my misconceptions and others as well. And I appreciate everything you've done, and I wish you the best on your new career at JPL, and I hope everything is going good for you down in Southern California. And we'll see you again one of these days. And thanks again, Dave. And I'll see you again next month. What's the date of next month's meeting, by the way?
Thank you. I wasn't sure if I mentioned that. It's Saturday, September 18th at 7 p.m.
Saturday, September 18th. Okay, very good.
Thank you.
Thanks. Good night, everyone.
Good night, Jim. Thank you very much.